Well, again, thank you for inviting me. It's always a pleasure to be here. So I'm going to talk about something a little bit different from what you've seen so far. In fact, I was asked to talk about adaptive optics, and I'm glad I didn't because you've heard a lot about adaptive optics today. So I'm going to talk about, it's back to optics, for one thing. It's going to be volumetric imaging in scattering media, so there is scattering media. So this is a very vast topic, volumetric imaging in scattering media, so I'm going to narrow it down a little bit. I'm just going to talk about fluorescence imaging in scattering media, and I'm going to pick a scattering medium. I know there's a lot of seismologists here, but you know, a bunch of rock, a mouse brain, it's all the same thing. So I'm going to concentrate just on the mouse brains here. All right? So there's a lot of challenges when you want to do volumetric imaging inside mouse brains. There's challenges. Well, first of all, you want to see a volume, and you want to see a large volume. So you want a large field of view, you want a large depth, but also you'd like to get reasonable resolution. When you're working with light, you'd like to get micron scale resolution. And of course, you want to also go fast, right? You want to, in fact, that's one thing that's different between looking at rocks and looking at mice. In mice, there's activity. You have to image that reasonably quickly. All right, so you want to meet all these challenges at the same time, and it becomes actually fairly difficult to do all four, to address all four challenges. All right, so first of all, if you want both depth and micron scale resolution, there's really the most effective technique to date is basically this thing called multi-photon microscopy. Now, all of you, I assume, know a little bit about multi-photon microscopy, but just as a reminder, there's a difference between multiphoton and one-photon microscopy. Again, the problem is you want to focus a laser beam in a scattering medium, and you want to generate a signal from the focus. The problem is if you focus in a scattering medium, a lot of the light doesn't make it to the focal spot. A lot of the light is scattered. And the problem with fluorescence, one-photon fluorescence, is that scattered excitation light can generate fluorescence if you use a one-photon interaction. On the other hand, if you use a multiphoton, a nonlinear interaction, the scattered light, the scattered excitation does not generate background fluorescence, and really the only fluorescence that you get comes from the focal spot, comes from the unscattered light. And so that's a rule of thumb. When you use multiphoton microscopy, only ballistic light, only unscattered light produces signal, and you have a very high contrast. You have very little background, so thus you have very high contrast. All right, and you get beautiful images like this. This is why it's so popular. You get images of neurons inside mouse brains, depending on how you label the mouse. You get, you can go fairly deep, maybe over 0.5 millimeter deep. It doesn't sound very deep, but this was revolutionary when it came out. You can get these kind of images at this kind of depth inside live mice. All right, so let's ask the question, well, exactly how deep can we go with multiphoton microscopy? Well, you can actually answer that question fairly easily, because if you know that only unscattered light produces signal, well, unscattered light, the decay, how much unscattered light is left after you propagate a certain distance, z, inside a scattering medium, it obeys the Lambert-Beer law. It decays exponentially. So there's less and less unscattered light that makes it at deep depths, and it decays with a decay length equal to the scattering length of light inside that tissue that you're looking inside. Scattering length is how far light goes before it scatters. All right, this very simple law tells you a lot. Actually, just looking at this law, you can figure out one thing. You can figure out that the maximum depth must scale this way. It must scale as LS times the log of everything else, right? So that's right there, just this one law tells you this. All other parameters are inside a log. And log is a function that's very flat. So all other parameters actually don't play a huge role. The biggest role comes from LS, the scattering length inside that tissue. All right, so let's start by looking at all the other parameters. Let's look a little bit more detail at this equation. The maximum depth penetration will look something like this. LS times the log of all these parameters. Let's look at these parameters one by one. Well, you have the fluorescent molecule efficiency. The brighter the molecule, the deeper you can go. The lower the detector noise, the deeper you can go. The more power you stick inside your sample, the deeper you can go. But again, they're all inside this log. What about this term right here? This is the collected fraction of generated fluorescence. You're going to generate signal from the focal spot, and that signal has to get out somehow. And it's generally assumed in multiphoton microscopy that the collection efficiency is constant, right? That no matter how deep you are, you collect the same amount of fluorescence. And that's one advantage of multiphoton microscopy. You can use these very big detectors to collect a lot of fluorescence. But it's not quite true that the collection efficiency remains constant. It remains roughly constant up to a limit. And that limit is basically defined by the field of view. FOV is the field of view of your microscope. So that field of view has a certain radius, and the collection efficiency is roughly constant up to that radius. And so, for example, if you're near the surface, if you're focused near the surface, what matters is the range of angles that you're collecting. So the fluorescence is coming out in all directions, but if you collect over a large range of angles, you collect more and more of that fluorescence. So near the surface, the collection efficiency scales as the numerical aperture of your detection squared, right? That's the solid angle of the angles that you're collecting. But once you go a certain depth, so you go deeper and deeper, you focus deeper and deeper, it remains roughly constant, this collection efficiency, but then it starts dropping after you go beyond this field of view of your microscope. And it drops basically with this scale. The deeper you go, it drops as the square of the depth, but also as the square of the field of view of your microscope. All right? Why is that? Why does it depend on the field of view of your microscope? The problem is, as you go deeper and deeper, a point source here starts not looking like a point source. It starts looking like a very large area. It starts looking like a pancake. So if you want to collect all the fluorescence, you have to look over a larger and larger area. Not just a larger and larger range of angles, but a larger and larger area. And so in this regime, when you're very deep, the collection efficiency depends not only on the range of angles that you collect, but also on the spatial scale over which you collect. So it's useful to have microscopes with actually large fields of view, with low magnification. You're looking over a large area. And for example, if you increase your field, so typically the field of view of a microscope is defined by some kind of field stop. If you get inside your microscope, take a drill and blow out the field stop, you can maybe expand your field of view by, let's say, maybe a factor 4. That gives you a factor of 16 increase in collection efficiency. Right? So if you increase your collection efficiency by a factor of 16, right, if you increase this by 16, that's equivalent to multiplying your laser power by a factor of 4. It's a lot easier to take a drill, blow out the field stop, than buy a laser that's 4 times more powerful. Right? What's this other last term right here? This is the inverse laser duty cycle. When you're dealing with, let's say, 2-photon microscopy, you need any nonlinear microscopy technique, you need to get a high local intensities. How do you get high local light intensities? You focus light in space, but it's also very useful to focus light in time. So for the same average power, here's an average power of, say, 8 photons per unit time. If you take those 8 photons and just reorganize them, focus them in time into pulses, you increase the amount of 2-photon signal that you generate. You increase it by this factor. For example, for standard lasers that you would use in 2-photon microscopy, this factor is about 10 to the 5. So you get 10 to the 5 more fluorescence just by reorganizing your photons into pulses rather than, say, a continuous wave. And let's say, so most people are using these lasers at 80 megahertz. They've been around for quite a while. But it turns out that if you just lower the repetition rate of your laser, you lower, you basically increase the distance, increase t, sorry. For example, let's say you lower it by a factor of 100. That would be equivalent with the same average power. You lower the repetition rate by a factor of 100 to, say, 800 kilohertz. That's equivalent to increasing your laser power by a factor of 10, right? So when you go deep, it's much better to use low repetition rate lasers. But again, all these terms are inside a log, right? So again, let me say that again. If you want to try to go deep, very deep in tissue, you're better off using lower repetition rate lasers. All right, and this was verified experimentally. For example, Winfried Denk demonstrated this way back in 2003, looking inside brains, and they could extend the depth by a factor of 2. They could go almost a millimeter deep just by lowering the repetition rate of their laser. But here you see something very interesting. As you go deeper and deeper and deeper and deeper, you might expect that the signal would just disappear. But if you look way down here, it turns out the signal doesn't disappear at all. Suddenly your image becomes uniformly white. And you're going like, what's going on here? The signal didn't disappear. Suddenly you just lost contrast. What happened? And it turns out that contrast is a huge problem, is another depth limitation I haven't talked about yet. So here's the issue again. Remember, only unscattered light generates signal. The unscattered light decays according to this Lambert-Beer law. It decays exponentially. That's a terrible law because it really decays drastically as you go deep. And the problem is, because of this decay, let's say you want to image something at this depth over here, you have to, there's less and less power as you go deep, and to get a reasonable amount of power at this focus, you have to dump a lot of power into your sample. So you have to dump a lot of power onto the surface of your sample to hope to get a reasonable amount of power at the focus to generate an adequate signal. Now, ideally, you would like this signal to be big compared to the background. The problem is you've dumped in so much power into your sample that near the surface you have a power density that will also generate signal. Actually it's background. This would be signal and this is background. This is still coming from ballistic light. It's still coming from unscattered light, right? So we're still obeying that rule of thumb, but the problem is unscattered light, you have such a high power density here that unscattered light will generate fluorescence. And so you get fluorescence both from the surface and from that focal spot. And the problem is you only have one detector. They can't separate, that one detector cannot separate these two. And so you've got this background which is detected at the same time as your signal. And the problem is as you go deeper, so here it's okay, the signal is bigger than the background, but as you go deeper and deeper, this signal decays, right? It decays drastically, exponentially, and you don't have to go very far before this background starts dominating the signal. And once the background starts dominating the signal, you don't see any structure anymore. That's where your image becomes uniform and basically white, right? You've got no structure. And so this is a huge problem. So how do you deal with this problem? Well, one way to deal with this problem is try to minimize the amount of light that's scattered. If you try to take all this scattered light and somehow redirect it towards the focus, then maybe you don't have to dump so much power into your sample, and maybe you won't have such a big power density here after all, and maybe you can reduce this amount of background. How can you do that? Well, maybe adaptive optics will help. So we've heard a lot about adaptive optics. I'm going to skip this slide. You kind of get the general idea. Use this active element to basically take that scattered light and somehow channel it towards the focus, so you don't need as much power. All right, so I have to show you this slide. This is like an obligatory slide. Apparently every talk has... so the only thing I want to say is kind of ironical. This paper had huge impact, but these guys had... they struggled really hard to publish this paper because nobody thought... as I think Ori said it, it wasn't supposed to work, right? It wasn't supposed... So they struggled to publish this paper. You know, they sent it to Nature, Nature Photonics, Nature Communications. You know, we all went through this list, right? Optica. And eventually, it got published in Optics Letters. And I find this, that this very high impact paper that they had to struggle like that, and they published it here, and it has high impact. I find there's a lot of poetic justice right there. All right, so again, the idea is if you have a lot of degrees of freedom in your correction element, you can actually get a correction. You can actually get this focal enhancement. And the key is the more degrees of freedom you have here, the better you do. And now you get elements with a lot of degrees of freedom, like spatial light modulators. All right, but there's still problems with adaptive optics, at least when applied to imaging in biological tissue. As Ori mentioned, typically takes a long time. You know, there's an optimization step that typically takes a long time. And one of the challenges that you need in biological imaging, you have to image fast. So this has been a kind of a problem, kind of a bottleneck. There's another problem. Well, this problem of typically taking quite a long time may be solved, though. I mean, people are getting more and more clever about how they do their corrections. One technique, for example, I like a lot is this technique called F-sharp by Ben Jutkiewicz. It's very similar to the RR matrix that Matthias was talking about. You measure the RR matrix, but you do it really quickly. And when you do that, you can start doing adaptive optics corrections fairly quickly deep inside tissue. So this problem of speed may ultimately be solved and may go away. But even if the problem of speed is solved, there's another problem, which Ori, of course, talked about, and that is that correction, the area, the range over which you're doing the correction, the isoplanatic patch, the memory effect, it's got a lot of names, it gets smaller and smaller as you go deeper and deeper. And you're only doing, as you go very deep, you're only correcting over a very small range. And one of the other challenges that we wanted is we wanted to do volumetric imaging over large ranges. So this is a bit of a problem. Here's an example. This is, I would consider kind of the state of the art in adaptive optics is techniques that Naji is using. Here she's correcting over a range of the isoplanatic patch. Looking at this neuron is about 30 microns, right? But if you look at the corrections, the adaptive optics corrections, the phase profile of the wavefront shaping that she used, it looks like this. Clearly, you can see here that the complexity of the aberrations were not that bad, right? Because she's correcting mostly spherical aberrations. So this is mostly aberrations that originated at that interface, the brain, say, water interface, right? So she's mostly correcting for surface aberration, and she has an isoplanatic patch of, say, 30 microns. The problem is, as you go deeper and deeper, the aberrations become more and more complex. And the phase corrections start looking like this. And this is a situation that Ori was talking about, where the complexity is greater than the number of elements you have in your correction element. And that's when you have this problem that the isoplanatic patch starts collapsing. And so this is a problem that I think is a big challenge, particularly in biological imaging. And so I would say that as far as adaptive optics is concerned, applied to biological imaging in the mouse brain, the jury's still out. How useful is it? All right, but let's go back to this formula. Again, all these terms that I talked about so far, they're inside the log. They don't play much of a role, right? Even if you increase this by a factor of 10, you take the log of 10, you don't get much, right? It's not a huge increase. And you can struggle to increase by a factor of 10, but that log kills your struggle, and it's very depressing. On the other hand, the maximum depth penetration scales linearly with the scattering length. And you might say, well, that's a problem, because I can't really control the scattering length. The scattering length is a property of the tissue that I'm looking at, and I don't have much control over that. But that's not quite true. It turns out you do have control over the scattering length depending on the wavelength that you're using to do the excitation. For example, here you're looking at, this is a mouse brain, and here these people at Stanford had this fluorescent marker. It was a carbon nanotube that generated very broadband fluorescence or light luminescence over a very large range of wavelengths, you know, from the near infrared to the mid infrared, right? And then they used filters and looked at the image they saw, and at these sort of lower frequencies, higher frequencies, smaller wavelengths, the scattering length is fairly short. And so you get all this blurring, and you can't see these blood vessels, so this is labeled vasculature. It's all blurred, right? But as they go to longer and longer, they change the filters. As they go to longer and longer wavelength, the scattering length of the tissue gets longer and longer, and thus the maximum depth penetration increases, and you get sharper and sharper images, right? As you go actually deeper as you go to these longer and longer wavelengths. And so this idea of going to longer and longer wavelengths was applied also, that was what I just showed you here, was just standard imaging, standard one-photon imaging, just a camera, right? A camera that's sensitive to the infrared. But this idea of going to longer and longer wavelengths was also applied to two-photon microscopy, and just by going from, say, 800 nanometers to 1200 nanometers, suddenly you can go now to 1.6 millimeter depth penetration. This was showed by Chris Hsu. You can even go even longer wavelength by going to three-photon microscopy instead of two-photon microscopy. Instead of having two photons generate fluorescence when they meet simultaneously, if three photons meet simultaneously, then you can use longer and longer wavelengths. And this is another idea, as Rory was saying, this is an idea that wasn't expected to work. Nobody tried this because nobody thought, you know, it was already hard enough to do two-photon microscopy, and everybody thought, there's no way three-photon microscopy is going to work. Chris Hsu had the temerity to actually try this, and lo and behold, it did work, right? It did work, and he significantly increased the depth penetration just by going to longer wavelengths, and that was the trick. Go to longer wavelengths. And so here's an example. That's that image I showed you previously. This goes, these are layers inside the brain. This one goes maximum, maybe you can go to layer 5 inside the brain, which is about 0.5 millimeter deep. This starts at layer 5 and keeps going, down about 1 millimeter, down into, it goes past what's called the white matter inside your brain, which is the very hard, it's like as far as light is concerned, it's almost impenetrable here, and they actually go beyond that, which is remarkable, just by going to longer wavelengths. All right, if you want to go deeper still, well, you've got a problem. I mean, so you can go 1 millimeter, okay, but if you want to go deeper still, then you somehow have to remove scattering altogether. So how can you do that? Well, you can maybe stick these rod lenses in your system. So Tomasz talked about this. You can start trying to miniaturize this. And you can miniaturize this. In fact, this was, for example, done by Mark Schnitzer. You can actually make head-mounted microscopes. This is a standard 1-photon microscope. But you can see there's this little rod lens that they poked inside the brain, which sort of moves all the scattering tissue away to look directly at the neurons that are fluorescent in front of this rod lens. Now, these rod lenses, as Thomas pointed out, they're not that small. You've got this mouse brain, which is a certain size, and the rod lenses are, maybe 1/10 of the mouse brain. So it's like having a telephone pole stuck inside your brain. And the problem is, as you poke these rod lenses inside the brain, they tend to crush the neurons right in front of the rod lens, right? They tend to crush the neurons that you want to look at. And so this can be a problem. That problem can be addressed by using not a rod lens, but for example, a little microprism. So if you poke a microprism inside the brain, then the thing that gets crushed is the neurons along the hypotenuse of this microprism. But that microprism acts as a mirror. So what you're looking is at the neurons, you look at them from the side. So you're looking at and often you prefer to look at the neurons from the side rather than from the top, because then you get these kind of structures immediately. Instead of en face, you're better off looking at them from the side. So here's an image of that. Here's the brain from the top, but here on the microprism, you actually see the brain from the side. And these microprisms can get pretty small. Here it's roughly the size of Lincoln's nose. Right? Okay. Just a small aside, I have to do a little publicity. What about dynamic range? Let's say you want to look at these neurons, right? You've got these neurons that you want to look at in tissue, and you've got these bright bodies, they're called somas. That's the body of the cells. And you've got these dimmer dendrites or axons or processes. And you'd like to see them both at the same time. You want to do very fast imaging, so you don't have time to adjust your gain. You'd like to see them both at the same time, but maybe your system doesn't have the dynamic range to see both at the same time. Maybe this saturates to see this, or if you look at this, then this is too dim. You don't have the right dynamic range. What can you do about dynamic range? Is there a way to fix the dynamic range of your microscope? So the way a standard scanning microscope works, multiphoton or confocal or whatnot, is you take a laser beam and you focus it in your sample and you generate a signal. As you're scanning the laser beam, the signal changes, right? You generate a signal and you detect that signal. And that signal can go up and down, right? If you're looking at a soma, it's very high. If you're looking at a dendrite, it's very low. And it's quite possible that you may not have the dynamic range to capture the full dynamics of your signal. So what can you do about that? Well, one thing you could do is take a feedback loop to feed back on the power. Instead of using constant power as you do in conventional microscopy, if you take a feedback and vary the power on the fly, as you're scanning, you vary the power to try to regularize this signal, to try to keep it more constant so that it's within the dynamic range of your detector. That can help ultimately. In other words, you're moving signal from the detection side, you move the signal to the illumination side. So there's the signal right there. So it is how you fed back to change the power, right? Well, that works very well, right? So here's a conventional 2-photon microscope. Take a laser beam, stick it in your microscope, look at your signal. If you just take a feedback loop and go from your signal and adjust your laser power, and this could be done just with a little tiny FPGA. You have to do it fairly fast. You have to do it on the fly as you're scanning. You can go from this kind of image. This is a neuron, the soma of a neuron. You can't even see the processes because they're too dim in your image. But if you do this feedback thing, in the same time, without losing any time, you can get this kind of image. So you can see, and you haven't saturated, right? You're still not saturating here, but now you can see a lot more structure in your sample. So you can increase the dynamic range of your imaging and go from, again, this is a Z-stack. You go from this type of imaging to this type of imaging with basically no loss of information, no speed penalty. It's a win-win situation, right? And I would argue that most people want this kind of imaging rather than this kind of imaging, right? All right, that was just an aside. That was publicity, so we worked on that. Back to volumetric imaging, which is the topic of this talk. What about speed? Remember, that was one of the challenges that we had to deal with. We had to go fast, right? So how can we go fast? Well, here's an early attempt at doing volumetric imaging quickly, right? This was done by Fritjof Helmken in 2006. To scan your microscope, the most common way to do it is these moving mirrors on galvanometers. Well, what they had was these moving mirrors that did this sort of spiral shape. They were both resonant in the X and Y, and they sort of breathed the amplitude of the spiral shape. And so there's a spiral that's expanding, breathing, and then they pumped the objective up and down, right? They moved the objective up and down so that they could probe a volume in their tissue using 2-photon microscopy. And how fast could they get a volume image this way? Well, they could get it as fast as they could move that objective up and down. Now you can imagine that an objective is a fairly heavy structure, so the fastest they could move this objective up and down was about 10 hertz. Right? So they could get volumetric imaging at 10 hertz with this technique. All right, that was back in 2006. That was an early attempt. It turns out now there are ways to change the focus of a microscope much faster and much simpler. For example, now you can buy these liquid lenses, right? These lenses are basically electrically controllable lenses where you just change the voltage and it changes the focal length of the lens. And you can do this quickly. You can change the voltage at about 100 hertz. So you can go up and down at about 100 hertz. Basically, you remove the inertia, right? You've got much less inertia here than you had moving an objective up and down. And so here you can bounce up and down. For example, this was also done by Helmchen, where they were bouncing up between two different focal planes at 100 hertz. So it's not quite volumetric imaging, but it's two-plane imaging at 100 hertz. Right? But it turns out you can even go faster still. Right? There's these things called tag lenses, tunable acoustic gradient lenses, also kind of liquid lenses, and they can scan even faster. They can do an axial scan at about 100 kilohertz, right? which is really fast. You're going from 10 hertz now to 100 kilohertz. And so it's an interesting situation. This was done by Meng Kui back in 2015. This was a situation where the scan in the z direction was the fastest of the three. Right? You're scanning in all three dimensions. Normally, X and Y are much faster than Z, but here Z was faster than X and Y. This is the first time that ever happened, right? And so they were getting volumetric imaging, well, at about a kilohertz here, right? The bottleneck was the X scan, right? The problem with this is that the range was not great, right? They couldn't scan over a long range. They could scan maybe over 100 microns or 140 microns, I forget. So this was a problem. What if you want to go to large volumes? Remember that set of challenges? There were 4 challenges. We want to see large volumes. We want fast, high resolution, but large volumes, which means you want to go deep. You want a large field of view. How do you do that? Well, one way to do that is just use a bigger gun, right? Just make a bigger microscope, right? So here's an example. This was done by Karl Svoboda. This microscope, you can't really see it here, but this thing is huge. It fits the whole table, right? It's enormous. The objective on this is the size of a coffee mug, right? It's a huge objective. It's a huge microscope. But it's remarkable. You can get images. By the way, you can buy this for, I'm not sure how much it costs. I never actually checked the price. It's probably like $1 million or something. You can buy it from Thor Labs. But here's examples of what you can see with this. So this was from the Svoboda lab. And they can zoom in and see these neurons. Right? These are neurons. They're tagged with a fluorescence marker that changes its intensity when the neuron becomes active. Right? And you'll see that these neurons will become active. And see, now the neurons are active. You're looking at the mouse thinking. Right? All these neurons are active. and they're focusing in and out. They go in deeper, and now they're focusing out. You see all the activity of the neurons, all these neurons, now they're focusing out. You see the blood cells, these dark regions are the blood cells, and then that was the surface that you just saw. Right? Two photon, yeah. And so here you see the blood cells in here. So, and look at the scale bar, 1 millimeter here, right? So they're looking over several millimeter scale bar with micron resolution. Now the problem is, they weren't doing this all at the same time. If you look very carefully, this image was not acquired at the same time. These are tiled images. Their field of view at any given time was only about this size. And they had to pan around they had to move the mouse around to get this. No, they didn't move the mouse around. What they did was they sort of bounced. So they have a potentially a large field of view, but what they did was to get the high resolution that they wanted, they looked at small zones at a time, and they just shifted that zone within that larger field of view and then tiled everything together. And the way they shifted the zone is they had another set of galvanometers to shift. They had one fast set of galvanometers to look at small zones at a time, and then they had a slower set to shift the region of interest very quickly. And they could also shift up and down in Z and left and right, etc. So they could shift volumetrically and then get these tiled images over large volumes. So this was quite remarkable. This came out in 2016. But there's a problem, right? The problem is, let's say you want to look at a large volume. So large in this context is maybe a millimeter cube, right? A millimeter cube is a fair chunk of the mouse brain, and let's say that's what you want to see. And let's say you want to follow the dynamics of neurons. Let's say the calcium dynamics. So you'd want a minimum speed of, let's say, 10 hertz. So you want to see a millimeter at 10 hertz speed. And you want your optical resolution of 1 micron cube. Now, if you run the numbers, there's a problem. You would need a sampling rate of 10 to the 10 hertz, right? 10 to the 10 hertz. That's really, really fast. The problem is scanners, typically the maximum scanning rate is only about 10 megahertz. You're 3 orders of magnitude off. Even if you were to increase the speed of your scanners, you'd be limited by the repetition rate of your lasers, right? You've got these pulse lasers, and typically the max repetition rate is about 100 megahertz, right? You're 2 orders of magnitude off. So you need at least 1 laser pulse per voxel here, right? To get a signal, and you'd be limited by the laser pulse rate. So you're at least 2 orders of magnitude off from technology is not good enough to meet those kind of specifications. So what's a microscopist to do, right? Well, how do you solve this problem? Well, one way to solve this problem, so there's 2 options. Well, there's probably many options. I'm just going to talk about 2. One of them is called targeted scanning or random access scanning. Is instead of looking at your entire field of view, let's just concentrate on the neurons of interest. Pick a few neurons, and let's just concentrate on those. And let's just scan, we're not going to have a space-filling scan, we're just going to have a scan. It's like a traveling salesman problem. You meet the neurons one after the other in a linear fashion. And so you reduce the amount of time significantly because you're not spending a lot of time looking at areas that you're not interested in, right? Here, most of the areas you're not interested in. So this was done just with galvanometers. You can just program your computer to visit the neurons of interest and skip the rest. And you can significantly increase the speed of your imaging, right? It's obvious, right? And here we were going 2 millimeters at 100 hertz. This is just 2D imaging. You can extend this to 3D. So we were just using galvanometers. Much better is work that was done by Angus Silver. Stéphane Dieudonné does this in Paris. A lot of people do it now. Turns out you can sort of randomly point a laser using acousto-optic deflectors. Right? Acousto-optic deflectors, they have no inertia. In fact, the limit to moving a laser beam around with steering mirrors or whatnot is the inertia of the mirrors. But acousto-optic deflectors, there's no inertia. So potentially you can go quite fast. You can move the laser point and you can aim it randomly in your sample quite fast. Not only can you aim it in 2D, it turns out you can aim it in 3D. You can put sort of a quadratic curvature on the phase profile of your acousto-optic deflector and change the focus as well. So you can address neurons one by one. Again, it's a traveling salesman problem, but here now in 3 dimensions, and they can visit a relatively large volume much quicker because they're not spending a lot of time looking at regions that are not interesting, right? And acousto-optic deflectors can provide a roughly about 100 kilohertz switching rate. You can go from one neuron to the next at about 100 kilohertz. So there's a couple of problems with this option of sort of random axis scanning where you just address the neurons of interest. One is you have to know where to aim, right? You have to know where those neurons are that are of interest. And so there's a whole calibration step involved. You have to take a volumetric imaging, a space-filling volume imaging. You have to figure out where the neurons of interest are. You have to program that in your computer, program that traveling salesman problem to visit those in the minimum amount of time. And so there's this calibration step to program your path, the path that the laser beam is going to take. Once you've done that, once you've programmed the path, well, you may have a problem because as you're looking at the animal, this animal is alive, right? So maybe it sneezes, maybe it breathes, maybe there's a heartbeat, maybe there's a hiccup, and the whole thing can move. The whole brain can move. Well, if the brain moves, you're screwed, right? Because that path that you programmed is the wrong path. So you'd have to reprogram your path. So you're very sensitive to motion artifacts, and you might see signals in your signal that in your detected light that aren't signal at all. It's just motion artifacts. So motion starts looking like signal, and it's very confusing. So you're very sensitive to motion artifact. You need this calibration step. Another problem is it doesn't scale very well. The acousto-optic switching rate is about 100 kilohertz. That's okay. If you want to go at 10 hertz, you can maybe visit 10,000 cells. Right? That's fine. But let's say you want to go faster than that, and I'll explain why you might want to go faster than that. Let's say you want to go 1 kilohertz. In that case, you could only visit 100 cells at a time. Okay, so back to this problem. Right? So this problem, we have a problem. So the one option to address this was random access scanning. Now I'm going to talk about the second option. The second option is, well, we wanted this. That's the specifications we want. If you want to, the problem is you can't meet all these specifications at the same time, so you have to take a hit on one of them. You have to sacrifice one of them. Let's say you do want your volume of 1 millimeter cube. Let's say you do need this speed to track the dynamics. Let's sacrifice resolution, because sometimes you don't need that 1 micron resolution. You just want to look at individual cells. Individual cells are 10 microns in size. You don't need 1 micron resolution to resolve individual cells. So what if we took a hit on resolution? And then we need less sampling, right? And then we don't have to sample as fast. So how can you undermine the resolution of your microscope? Well, the resolution of your microscope is defined by the standard classic laws of optics, of a lens. The resolution in a transverse direction depends on the wavelength, and it depends on the range of angles that you're using to create your focus. It depends on the NA, right? The larger the range of angles, the tighter the focus, and the better the resolution along X. Now it turns out the resolution along X and the resolution along Z are not independent. They're correlated, and they obey these kind of laws. So this scales inversely with NA, this scales inversely with NA squared. Right? So basically the upshot is high NA, the larger this number, the smaller these, the higher the NA, the smaller these extents, and the better your resolution. So if you want to lower the resolution of your microscope, all you need to do is lower the NA of your illumination, right? So you use a smaller range of angles, and then your probe volume is larger. And so how much larger do you want to make it? Well, let's say you've got these neurons. Well, maybe the lateral extent, you'd like to fill the neuron. But the problem is if you do this, so you've adjusted NA so that delta X is roughly 10 microns to fill the neuron. The problem is if you do this, the delta Z is very, very large, right? Because you lower NA, this goes down, but this goes up, but this goes up by a lot. And so this might be a problem. First of all, it's very inefficient because you're exciting. There's a lot of excitation going on here that's not even looking at the neuron. Second is if there's another neuron above or below, there would be, you'd be confused as to which neuron you're looking at. So how can you address that issue? How can you generate more of an isotropic resolution with your microscope? The point is, well, I guess the solution is we have to get away from these laws of what defines delta x and what defines delta z. And there's a very simple way to do that, a very clever way to do that. It's called temporal focusing. So temporal focusing is, it was first shown by Jaron Silberberg and Chris Schuh basically simultaneously in 2005. So the idea is here, here when you create a focus with these, when you have a multi-photon microscope, 2-photon microscope, 3-photon, etc., you need pulsed illumination. To get pulses in time, you need many frequencies, many colors to generate narrow pulses in time. So this laser beam has many, many colors. And all the colors are basically, the spread of colors is basically uniform here. Right? So you have pulse, 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 and that pulse is focused and then defocused. So the idea of temporal focusing is to spread those colors in space, right? With a grating. You can do it with a prism or a grating. You spread the colors in space so that all those colors that were used to make those narrow pulses are now spread in space. So if you look at any point in space here, well, here you only have red. You don't have a huge range of colors. You just have red. Here you only have blue. You don't have, again, you also don't have a huge range of colors. So here, if you only have red, you cannot create a pulse with a single color, right? Here too, you cannot create a pulse with a single color. Actually, anywhere here, you cannot create a pulse because you only have a single color. And you need many colors to create a pulse. So when you've spread those colors in space, you've spread the pulse in time, right? Because you don't have enough colors to focus that light in time, right? Except for that point where all those colors converge at the focus. When all the colors converge at the focus, all the frequencies converge, and then now you can get this narrow pulse in time. This is called temporal focusing, right? So why temporal focusing? Because it's a focus in time. Here it's defocused in time, focused in time, and defocused in time, right? And in this way, you can get a much more isotropic resolution, right? You can get you can get roughly the same resolution in X and in Z, okay? This technique was adopted by, for example, Ali Pasha Vaziri. He calls it sculpted light. So again, you have to spread the colors using a grating, and then they get recombined at the focal plane to give you this temporal focusing. And his resolution in X and Y are roughly the same. So he's got roughly isotropic resolution. But the resolution is not a micron here. It's more like 5 microns, right? So 5 and 10. So basically the size of a neuron. So you don't have to, you can scan much faster because you don't have to look at, your pixels are much larger, right? So you don't have to scan, you don't have to collect as much information. Your data rate is much smaller because your pixels are larger. And you can, scan a volume of, say, 0.5 millimeter by 0.5 millimeter by 0.5 millimeter. You can scan that at, well, here was 3 hertz. Well, you couldn't do that before. Now suddenly you can, right? Actually, he's going faster now. This is even 3 years, and things change. So I think he's going almost 10 times faster now. Okay, but let's say you want to go faster still. Right? If you want to go faster still, another way to get around it is to, well, forget about volumetric imaging. Forget about volumetric standard. Ideal volumetric imaging. You have resolution. You have pixels, voxels that are 3-dimensionally resolved. What if you decide to sacrifice resolution along 1 dimension? One way to do that is, so here's standard volumetric imaging where you have 3-dimensionally, you have basically a volume would be a stack of 2-dimensional planes. And each one of these is an optically sectioned plane. Each one of these is 3D resolved. One thing you could do is basically sacrifice resolution along the Z dimension. And you can do that by using wavefront shaping to generate very elongated point spread functions. Oh, I thought he was going to tell me I have 5 minutes left, because that would have been very worrisome. All right. So you can use wavefront shaping to generate very elongated point spread functions. It's not like you're not seeing from an extended volume. You see information from an extended volume, but all that information is projected into a 2D plane. And now you can go quite fast because you don't have to scan along the axial direction. You integrate along the axial direction without scanning, right? One wavefront shape that has become very popular is basically an annulus in the pupil will create what's called a Bessel function, an extended sort of shard of light in the z direction, and you can extend this maybe a couple hundred microns and get images like this. This was done by Nagy, for example, where now it's only a 2D scan, but integrating over z, and here would be a standard volumetric imaging of neurons where color encodes depth. So you can see neurons are at different depths with a standard microscope with 3D resolution. But here now where you have extended resolution in z, you can take, whoops, I keep messing up here. All right, now I'm confused. All right, with z, with extended range in z, you can see all these neurons basically at the same time with a single 2D scan. So you have all this information. You sort of lose resolution. You don't know what depth these signals are coming from, but maybe you don't care, or maybe you know that a priori. Maybe you know the depth a priori because you've taken this image a priori, so I know that this is at a certain depth, this is at a different depth, etc. And you can get images like this, right? In a single 2D scan, you get information from a range of volumes, right? These neurons are coming from these flashing neurons are coming from a different volume, but you've acquired them in a single 2D scan. So one problem with this is you have this very extended illumination. It's very inefficient. It's a very inefficient use of laser power. So you cannot go very deep with this technique. A more efficient use of laser power is not using these very long extended point spread functions, but use point spread functions that are sort of focused, simultaneously focused at multiple planes, right? Instead of spread over multiple planes, they can be simultaneously focused over multiple planes, and you can program that into your microscope using wavefront shaping, using spatial light modulators and whatnot. And you can get, so the problem is, again, when you take an image, you actually don't know what depth your signal is coming from. It might be coming from two different foci at the same time. In fact, it is coming from two different foci at the same time. So how do you know which focus you're looking at? You don't, because you only have a single detector with this thing. So you may need statistical methods. If these neurons are blinking, you can separate them out in time using statistics and whatnot. All right, I've talked a lot about two-photon techniques. Again, but the problem is two-photon is a scanning microscope. So you rely on these scanners. Even if you have a 2D system, you rely on scanners, and the scanners typically only deliver maybe 10 megahertz sampling rate. Cameras now are amazing. These scientific CMOS cameras, their sampling rate is 100 times faster than the fastest scanner. And so potentially cameras can go much faster than scanners. And when you use cameras, we'll typically use them in, say, one-photon microscopy techniques. So where would this be useful? You still want to get optical, let's say you do want three-dimensional resolution. One way to do that is to use what's called light sheet microscopy. Instead of illuminating your sample from above and having background from above and below the focal plane, what you could do is illuminate it from the side with this little thin plane of light, and you're only illuminating this one plane, and this way you don't even generate background above and below the focus because there's no illumination above and below the focus. This only works, of course, if your sample is relatively transparent so that you can maintain this nice sheet of light as you travel through the sample. And you can imagine that in mouse brain it's not very effective. First of all, how are you going to look from the side? How are you going to illuminate a mouse brain from the side and look from the top if there's a skull around it? So you can have these contorted geometries where you come in at 45 degrees, you come in here and then you look from the side. But again, still the problem is you're going in thick tissue, so it might work near the surface where you get relatively resolved neurons, but as you go deeper and deeper, the light sheet gets broader and broader, and you don't get this, you don't get axial resolution anymore. You don't get good sectioning. Still, people have improved on the speed of this, for example, using a single object. So, this was kind of complicated, this setup, where you came in with an extra mirror, etc. You can now do it through a single objective, for example, where you excite the light sheet at a tilted oblique angle, and you detect all sort of oblique angle from the same objective, and then you sort of scan this light sheet by rocking it back and forth, and you can get volumetric images this way. This is called scape microscopy, but there's other ways to do this. The problem is if you want to get a volume, you still need to move this plane, and you still need to acquire a few camera frames, right? So that may be too slow. And there's certain cases where it will be too slow. One example is most people, well, so far in neurobiology, when you look at brains, the most common signal to look at is the calcium signal. There's calcium indicators, they go up and down, or they're a surrogate indicator of neural activity. And the dynamics of these indicators are roughly, 100 milliseconds, they go up and down. And so if you image at 10 hertz, you're okay, right? You can see the dynamics of these indicators. But nowadays, if you really want to look at the neural activity, you'd like to look at the voltage, the electrical activity of the neurons. And nowadays, what's coming online are these indicators that directly probe the membrane voltage, the voltage between the inside and the outside of a neuron. And these are very fast. The voltage spikes up and down very quickly, and the probes that monitor these voltage changes are very quick. They respond in a millisecond, 1 to 10 milliseconds. So you need to go much, much faster now, much, much faster if you want to see the dynamics of these over a large volume. You need to go in the range of kilohertz. Now you want kilohertz imaging. So how can you go very, very fast? Well, one thing you could do is you could use these. You could forget about volumetric imaging, and you can use this sort of extended depth of field imaging, and you can do that with wavefront engineering. You can use a Bessel beam wavefront, or you can use these other types of wavefronts. The problem with Bessel beam, I'm back to one photon here. If you use a Bessel beam illumination with one photon, it doesn't work very well. The power there's very little power at the focus. There's a lot of power outside the focus. But you can use other types of wavefronts, other types of point spread functions that are uniform along Z, that are spread along Z. One example is a cubic phase mask. This was done by Dowski. It's also done by Raphael Piston now. You can use what's called a layer cake mask that also spreads the point spread function along Z. The problem is the spread that you get is maybe only maximum 10 times the depth of field of your microscope. So let's say the depth of field of your microscope is a couple microns. This would go to maybe 20 microns, right? So it's not a big spread. It's not a big volume that you'd be probing with these phase masks. I call this static pupil engineering because there's another way to do pupil engineering, and that's using a changing pupil with time, right? So let's say I have a microscope that's focused, and I very rapidly change the focus. So it's like I have my focus knob, and I change it much, much faster than the camera exposure time. So I'm sweeping the focus in Z faster than my camera exposure time. Well, that's equivalent to having a long focus, right? Because I'm integrating over Z, right? And you can do that. Now there's these elements that can do these very fast sweeps. I talked about the tag lens. I talked about the liquid crystal lens. But there's another element, this deformable mirror. This is a MEMS device, I forgot what MEMS stands for. Basically, it's these little actuators that you can pump up and down at 20 kilohertz rates, and you can change the focal. But you can put a parabolic profile. It's basically a mirror. So it's the mirrors they use for adaptive optics. You can put a parabolic profile and focus at different depths at 20 kilohertz rates, right? And I was hesitant to use these devices initially because I knew that the stroke on these, the maximum excursion that these MEMS mirrors could take was only, at least the ones I have to use the mirrors from Boston Micro Machines, by the way. I have no choice, so it has to come from Boston Micro Machines. And these have a stroke of, maximum 10, 12 microns. And I thought, well, a 10, 12 micron stroke, that's not going to give me a very large focal range, right? But it turns out that's not true. If you just run through the calculations, you can get a much larger focal range than I had expected. You can extend with 10, 12 micron stroke. You can get an extension if your depth of field is maybe a couple microns normally with your microscope. You can extend that depth of field 50 times. So whatever the depth of field of your microscope, you can extend it 50 times using a deformable mirror, right? And you get images like this. This is these are fibrils and it's tissue, but tissue paper, not biological tissue. And you can see some fibrils are in focus. A lot of them are out of focus. This would be a standard image. If you take a standard image with a one-photon microscope, you've got in-focus light, and this is the problem with one-photon microscopy. You don't reject the background. So part of your image is in focus, a lot of your image is out of focus. Now, what I'm going to do is very quickly, in a single camera exposure time, I'm going to scan the focus. And what do I get? I get these images. Now, it looks like I've actually done worse, right? This image looks worse than this. But if you look at this image carefully, you realize that it's a very strange image. Because here you have part of the images, part of the structures here are in focus, and some of them are out of focus. Here, all the structures are equally in focus and out of focus. So this is a strange image. Everything's equally in focus and out of focus. Why is that? Because if I have a structure here and I'm scanning the focus, at one time, the structure was in focus. At all the other times, it's out of focus. But it's here, same thing. It's out of focus, then it's in focus. No matter where it is, at one time it's going to be in focus. At all other times, it's out of focus. And so I get a very strange point spread function, a 3D point spread function. If I have a standard microscope, the optical transfer function, the transfer of spatial frequencies from the object to the image, when it's in focus, it's very broad. I see a lot of structure. I transfer very large transverse spatial frequency from the object to the image. But when I go, all the out of focus structures, I don't transfer the large transverse spatial frequencies. All I see is the very low frequencies. I get a very blurred image when it's out of focus. So I have a very different transfer function when the object is in focus versus when it's out of focus. And this is a problem. If I want to do deconvolution and all my structures have different transfer functions, I have a problem. On the other hand, if I do this extended optical transfer function, everything, no matter what the depth is, they have the same transfer function. They're equally in focus and equally out of focus. This is the in focus part down here, which has these broad wings, and the out of focus part is this narrow peak, but they're equally in focus and out of focus. So everything shares the same optical transfer function. And if they do that, it makes deconvolution actually trivial. It's the same point spread function for everything, the same optical transfer function for everything. So I can deconvolve this very easily and recover an in-focus image throughout my volume. But there's still a problem. Actually, how much time do I have left? Okay. Good. Yes, good. There's still a problem. 1 hour and a half is very long, actually. Okay, but okay. The problem is with this extended depth of field imaging, as I said, sometimes these objects are in focus. A lot of times the objects are out of focus. The larger my volume, the more out of focus light I have and the less in focus light. Well, I have the same amount of in focus, but the more out of focus light I have relative to the amount of in focus. And so I start losing contrast. So here's an example. What am I doing? Here's some kind of tissue structure. What am I doing with extended depth of field? Basically, I'm taking an image, 2D images, at this depth, at this depth, at this depth, at this depth. At all depths, some of the structures are in focus, but a lot of the structures are out of focus. And then what do? I just integrate them. I add them all up, right? And my final extended depth of field image looks like this. Everything's equally in focus and out of focus, but the larger my volume, the more out of focus light I have, right? So my contrast goes down and down and down. And that becomes a problem with deconvolution because the noise from my background starts making deconvolution problematic. So is there a way to get larger and larger volumes and decrease the amount of background that I have in my system? And it turns out, yes, there is. If, while I'm doing my focal scan, if I pattern my illumination such that at every depth I'm only illuminating the structures that are in focus, right? So imagine I did that. Imagine I had, and there are, spatial light modulators or these DMDs, the MEMS ones, they can change their patterns very quickly at 20 kilohertz, right? At 20 kilohertz, I can change this pattern. And so at each depth, I can change the pattern and just look at the objects that are in focus. And in this way, I generate much, much less background. This is my final extended depth of field image if I didn't have pattern illumination. This is my final extended depth of field image if I do have pattern illumination. Why is this so much better? It's got a much higher signal to background ratio because I'm generating much less background here. If I don't have pattern illumination, at every plane I generate a lot of unwanted background. Here I'm generating a much less unwanted background. And I get much higher contrast without taking a speed hit. Of course, I need to know where those neurons are that are in focus, right? So it's kind of like random access scanning. I need to know what's in focus at every depth. So I need a pre-calibration step, and at every depth I have to figure out what's in focus. And there are standard ways to do that with microscopes. There's this technique called structured illumination microscopy, where you illuminate your sample with grid patterns, and then you move the grid around. So here you're illuminating with a grid, and you can see wherever you see the grid, that's structure that's in focus. Wherever you don't see the grid, it's because that grid has been so blurred that it's out of focus. And so what you do from these three images, you extract what you see in the grid, and thus you're extracting what's in focus. And so you do a little bit of math, and you can figure out at every depth what's in focus, and then you program your DMD to illuminate only those objects in focus at that depth. And you do this at every depth. You have all these patterns, these different patterns at different depths. You put them in your computer, and then when you do it, then afterwards, when you're doing the very fast scan, you just run through those pre-stored patterns, those patterns that you stored in the computer. And you can go extremely fast, and you can get images like this. This is a quasi 3D image, right? These neurons are at different depths, right? But I see them in a single shot, right? And I see them with much, much better signal to background ratio here with sort of targeted illumination than here. And I get much better signal to background ratio. Now here I'm scanning up and down. We used a liquid lens. We could have, in principle, used a deformable mirror to go at kilohertz imaging rates. And this is just not, it's not just cosmetic. The problem is if you have a lot of background like this and you want to look at the change, if you have two neurons next to each other and this neuron's active, but the blur of this neuron is superposed onto the signal from this neuron, it looks like this neuron might be active. So there's crosstalk. There's blur-induced crosstalk when you do imaging of the dynamics of these neurons. And if you remove the blur, you remove this crosstalk. You remove the correlation, the spurious correlations between neurons, and get much cleaner signals. All right. But extended depth of field is still a couple problems. So potentially you can go very fast. Potentially get volume images very fast at kilohertz rates. If we combined our DMD with a deformable mirror, we could get kilohertz rates from a fairly large volume with relatively good signal to background ratio. We haven't done that yet. We may go there. There's a few drawbacks here. Again, we lost our axial resolution. It requires that pre-calibration. This is the biggest drawback. It requires this pre-calibration, which is time-consuming. And if you need a pre-calibration, if you need to know where those neurons are that are in focus beforehand, and if there's any movement, then you have to reprogram your system and use different patterns. So we're very, we're susceptible to motion artifacts with this system. But the biggest problem is this is a one-photon system. It's a camera-based system. It uses wide field illumination. It's a one-photon system. So we can't go very deep. There's always going to be a certain amount of background. We can't go very deep. And the reason we can't go deep is because we don't reject the background very well. We reduce the amount of background, but we don't reject it, right? How do you reject background? Well, microscopes that reject background are called optical sectioning microscopes. They don't, either you don't generate background or you reject it physically from your detector. And so if you really want better contrast, if you really want to reject the background, you need a truly optically sectioning microscope. And so the classic optical sectioning microscope is a confocal microscope. Right? This has been around for decades. And the idea here is you don't just take an object and focus the light onto a camera. What you do is you focus both the illumination, so it's a scanning microscope, where you focus both the illumination and detection. So you take a laser beam, you focus it into the sample, and then take the signal that you've just generated and focus it into your detector. And the way you focus it into a detector, you put a pinhole in front of your detector and just detect the light that comes through that pinhole. And if you do that, if you have high NA illumination, in other words, a nice focus on your illumination and a nice focus on your detection, high NA detection, then you get a very small, three-dimensionally confined probe volume. So most of you know this, but I know some of you aren't really in the optics background. So The idea is you superpose two foci. This is why it's called confocal microscopy. There's two foci that are superposed. And if you multiply those 2 point spread functions, you get a very nice confined 3D voxel of information. It's confined in 3 dimensions. So the problem is, if you want to do volumetric imaging with this microscope, you have to move that voxel in 3 dimensions. It takes a long, long time. Right? So how can you do better? How can you go faster? Well, one way to do it that we looked at is you can do this, again, this sort of wavefront engineering, but there's a very easy way to do wavefront engineering, is to have very long, extended focus. Right? You could use either a Bessel beam, but better than that is just reduce the numerical aperture of your illumination. Right? If you reduce the numerical aperture of your illumination, right? Right, so we have a narrower range of angles to focus our light. Our excitation becomes long, extended in Z. Right? We still use high NA detection, so we're still collecting over all the fluorescence angles. So we still have a high NA on the detection side, and as a result, our probe volume is smaller than the excitation volume. Right? So we're looking over a region that's smaller than the region of illumination. But what's nice about this is, where is that probe volume? That probe volume is kind of defined where this pinhole is. If I move this pinhole, I move the probe volume. Right? And if I do that, I can sort of parallelize everything by using reflecting pinholes. So that this bottom pinhole, the first pinhole sees the bottom probe volume. Whatever misses this pinhole gets reflected to the next pinhole, which is a little bit further, which looks at a higher pinhole that's a little bit higher, 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 and so forth. And so you can fill that excitation beam, and you can see all those probe volumes within that excitation beam at the same time. So basically, you're looking at all these planes simultaneously, right? And what's nice is it's very light efficient. You haven't lost any light. Whatever light missed here, you eventually, it makes it into one of the pinholes, right? And you're collecting over the large range of angles, so you haven't lost any fluorescence light. And so you can get these simultaneous, this is just 4-plane imaging, and you can get, and it's very large field of view. We have 1.3 millimeters. We can see, this is a tick, right? This is a tick. We have a big problem in the northeastern United States. There's ticks all over the place. So this wasn't hard to find, this sample. And you can see, so this is the head of a tick, and you can see, they're autofluorescent, it turns out. You can see the different layers, the different heights in a tick simultaneously. So this tick was fortunately dead, so we didn't have to go that fast, but this was done at video rate. Right? We didn't really need video rate, but this was done at video rate. Oh, and you can colorize it if you want. This is C. elegans, and you can see this thing, 4-plane imaging. This was done, work by Emery Badon, by the way, who was, many of you know. So he was a postdoc in my lab and now left. C. elegans, you can see the neural activity, so you can see, so the color here is depth. So we have multiple depths at the same time, and you can track these again at video rate. Our resolution is not quite the micron level resolution, but it's good enough. It's 2.4 microns. It's easily good enough to resolve individual cells. And here's in brain tissue. The problem is it's a confocal technique, so it doesn't go that deep. So if you really want to go deep, you have to be a little bit barbaric. You have to, dig a little bit of the brain. So we're working with Shui Han, and so if we this is looking fairly deep in the brain, but we cheated. We took a lot of the scattering medium away. And you can get images like this. So this is over 1.3 millimeters. These neurons are at different depths. So here's the depth. We could see almost 1,000 neurons at the same time, all of them at different depths simultaneously, video rate over about a millimeter squared. And you can do these maps, etc. You can also extend it. This is 8 volume imaging, where you take chunks of 4 and then move it quickly, 4, 4, 4. So our frame rate is not quite as fast. We've halved the speed, but we've doubled the extent in Z. Okay, last thing I'm going to talk about. So it's simple, no speed penalty, very easily configurable. You can have high resolution, smaller field of view, or low resolution, larger field of view. Light efficient, we're not losing any light. Why is it light efficient? It's because the same light is being used to probe each plane. It's not light, if light misses one plane, it goes to the next plane. So it's the same light. So with the same amount of power, we get 4 planes, whereas in the past, you only get 1 plane. Right? The drawback is that the depth penetration is only modest. It's only a few hundred microns. Why? Because it's a 1-photon technique. It's a confocal technique. And as I said at the beginning, if you really want to go deep with relatively good resolution, really the only way to do it is multiphoton. Right? And so does this technique, we call it multi-Z, does it work with multiphoton? And it turns out, no, it doesn't. And why doesn't it work with multiphoton? It's for that reason I talked about before. If you go beyond the scattering length, so here, if you're looking at a depth that's within the scattering length, that light comes out in straight arrows, straight rays, right? And you can focus that light in a pinhole. But if you go too deep, a point source starts looking like a big pancake. And if it's looking like a big pancake, then you can't focus it into a pinhole very well. And you've got a big problem. So basically, never use a pinhole when you're doing 2-photon microscopy. You've undermined the advantages of a 2-photon microscope. So we can't use this pinhole trick. So we need another trick. We need a trick that's not on the detection side, but that's on the illumination side of our microscope. And so randomly we thought, well, what about temporal multiplexing? So temporal multiplexing, let me just briefly explain how that works. This is a standard 2-photon microscope. You take a laser beam. Remember, the laser beam comes out, the laser light comes out pulsed. So it's pulsed light, and we focus it into at a particular depth, and we generate fluorescence. And because the laser beam, the laser is pulsed, the fluorescence comes out pulsed, right? And the separation between 2 pulses is roughly 10 nanoseconds if you have an 100 megahertz beam, right? So 10 nanoseconds. So multiplexed, temporally multiplexed 2-photon works as follows. Let's take this, each pulse, and let's split it in 2. Right? You split it in 2 by using this 50-50 beam splitter. You send half of the light through a longer path than the other half. So you take this pulse and split it in 2, and the separation depends, the time separation depends on this path length difference between this and this. And you can separate them so that the separation is a few nanoseconds. Right? And if you do that, then the fluorescence from a single pulse now gets doubled, right? There's 2 pulselets that hit my plane here, and so I get 2 fluorescence pulses out. Right? And you might say, well, what's the point of that? Well, the point is, if I now put a lens in one path so that these paths focus at different depths, then each one of these pulses, pulse 1 and 2, focus at different depths. And so these 2 fluorescence signals, they come from different depths. And these are separate enough that I can distinguish them with my electronics. There's fast enough electronics that I can distinguish them. And they're separated enough that this exponential decay of my fluorescence is not a problem. There's not too much bleeding from one pulse to the next. So I can distinguish them. You can buy detectors that are fast enough now. You need nanosecond resolution on your detector, but that's standard now. You can get that. Technology exists. The only problem is if you want more than 2 planes, it gets more complicated. You have to split your beam into many, many paths, and it just becomes very complicated. Not only does it become complicated, you have a problem with power, right? You start losing power. You can't do this very efficiently by maintaining all the power in your system. So how can you get multiple planes? Well, one way to do it is to go back to basics and look at this configuration again. But instead of using a feed-forward technique where you split the beam and sort of feed it downstream from your laser pulse, what you could do is do this loop. Now, you've heard about reverberation. You just heard about reverberation last talk. We call this reverberation multiphoton microscopy, where a pulse basically goes in this loop, this cavity, right? And half of it goes in the loop, half of it doesn't. So half the pulse doesn't see the loop, goes right through, there's half. Half does, but then every time it hits this 50-50 beam splitter, half comes out. So you get half, a quarter, an eighth, and they're all separated by the length of this loop in time. And the length of the loop is, a couple meters, so these are separated by a few nanoseconds, right? So the problem is, okay, and so what do? You put, again, there's a lens in this loop, so that every time the pulselet goes through this loop, it sees the same lens over and over. And when you see the same lens over and over, it's like you add the focal length. Every time you're adding the focal length. So it's effectively like increasing the focal length of your lens. So each pulselet here is focused to a different depth. Now you might say there's a problem here because the first one I don't have the same power per pulse. And you might ask, well, what am I going to see with this system if each pulse has a different power? Well, the thing is, I haven't taken into account the fact that I'm looking in scattering media. Right? In scattering media, again, this is a multi-photon microscope. Only the unscattered light generates signal. So to look deep, I need a lot of power, right, to generate the same amount of signal as if I look shallow. So this actually adjusts the power automatically. Right? And if I adjust the separation between two planes, and I can just do this using the lens here, I can adjust the separation between two planes such that with this decay law, 1/2, 1/4, 1/8, I get basically the same fluorescence from each plane. And so what's the optimal separation? The optimal separation depends on the scattering length times log 2. So the scattering length in brain is maybe 100, couple hundred microns, multiplied by that log 2. So the delta Z is about 100 microns. So in one shot, with one pulse, one pulse, I basically, it's like an extremely fast axial scan. I can scan through these layers very quickly in a single shot. Right? And you might say, well, there's a problem with this, because I go all the way to the surface. Right? First of all, how does this stop? You might think this keeps going, but it actually stops when the plane comes out of the sample. Right? Eventually, the planes are going to come out of the sample, and then I generate no fluorescence. So eventually, it's going to stop. So you might wonder, okay, so I might be going deep, and I go all the way up to the surface, and you might think, well, I'm operating at, my lens is designed, my objective is designed to look at a particular focal depth. Are there going to be aberrations when I start looking at different focal depths from what my lens is designed for? Well, there's two ways to address that. The easiest way is to ignore that, right? To ignore that, and to make measurements and show that it's not too bad. There are aberrations. And they get, in X and Y, really those aberrations don't affect us much. In Z, they do affect us a little bit more, but it's still not too bad. Another way, potentially, could be to put some kind of aberrating deformable mirror here that sort of corrects a cumulative correction every time you go through the loop, and that cumulative correction would I'm assuming that the aberrations are cumulative as you go away from the focus. So that's possible. I don't know if that's true or not. So we haven't looked at that yet. But in any case, we can go, for example, this is 6-layer imaging. The problem is, well, we had laser. This is vasculature. So each color corresponds to a single depth. This is a single shot. And if you then do a scan, but now all we have to do is scan from here to here, and we get the whole volume at the same time. So we're just scanning we're just scanning 100 microns, and you get a volume of 600 microns simultaneously. And you can get these kind of images, so forth. This is simultaneous calcium. This is 4 layers. You can see the dynamics. Blah, 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 spontaneous activity. This is evoked activity, 3 layers, simultaneous. So the mouse with breathing and odor, and suddenly the neurons become active. And you can see that we're looking at very different neurons in each case, but simultaneously. Or quasi-simultaneously, within a few nanoseconds. And so that. Okay, reverberation MPM, very simple. You get many, many layers, and many layers without adding complexity. It's the same system. You can get an arbitrary number of layers. No speed penalty. We're going still video rate scanning. Increasing the number of planes does not increase complexity. So it's the same system. And what's actually very we didn't realize how beneficial this was, but it turns out that if you want many planes or many zones of interest from your sample, you're much better off stacking those zones of interest axially than laterally. It's much more power efficient to stack them axially than laterally. And here's what I mean by that. Let's say I have a standard 2-photon microscope, and I image as deep as I can go, right, with all my power of 1, and that's as deep as I can go. What if I want 2 planes? Right? What if I want to do temporal multiplexing with 2 planes? Well, then half the power, and I want to spread those planes laterally. Well, half the power has to go here, and half the power has to go here. And I take a hit of delta Z of about 100 microns. I can't go as deep with half the power, so I lose about 100 microns. If I want 10 planes laterally, each one of these would be 1/10 of the power, right? That would be very bad. But here, with the same amount of power, if I stack them vertically rather than transversely, here I can only get 2 planes. Here I get many planes. I can get 10 planes, 20 planes, depends on how deep I go. Why? Because it's still the same amount of power. If I add all these numbers up, it's still 1, right? And yet I still get the same amount of fluorescence, right? Same amount of fluorescence from all planes, but here there's 10 planes for the same amount of power as I would have had 2 planes if I did the transverse separation. So I can, with the same amount of power, I can almost go as deep as a standard multiphoton microscope. I just took a 100 micron sacrifice in depth, but when you're going about a millimeter deep, 100 microns is not a huge sacrifice for the same amount of power. So where do we want to go? Well, again, I told you at the very beginning that ideally we'd like to have a low repetition rate laser that's high power. That's not what we had. Unfortunately, we had a high repetition rate laser that's low power. So we had to artificially reduce the repetition rate of our laser. It was a big mess. Ideally, we'd like to go to 3-photon microscopy, to go very, very deep, because 3-photon microscope lasers are intrinsically low repetition rate. And that's it. These are the people I mostly want to thank. So this is my team right now. Actually, this is kind of old, too. I mostly want to thank the people in red. So these are the people I've collaborated with. Ansantenac, for example, did a lot of the convolution work. Tom Bufano, Ian Davison. Devin did all the reverberation microscopy work. He's a student of Tom Bufano's, but I've stolen him from Tom. So that's great. And Emery did all the work on the multi-Z, and Tim, Sheng, and Will. Thank you.